So good morning to all of you. I welcomes to all in our lecture series on quantum mechanics. In our last two classes we are discussing about spreading of Gaussian wave packet. So today also we are going to continue wherever we have been left. Okay. So in short I am going to discuss about last two classes whatever we have been discussed. So we discussed that suppose this is a wave packet where that means having both wave nature and particle nature. Suppose this is the particle and its superposition of waves will be like this, and this will be called as the wave packet, and this will be nothing but your real part of the wave function. And this real part of the wave function, if we are going to consider this much only, it looks like a Gaussian function. That means suppose we are going to be consider a Gaussian function, this one, and we have to draw a this function in your coordinate in your coordinate system. Then we are going to find out this type of graph, which will be alike with your real part of the wave packet. Okay, so hence wave packet can be represented by Gaussian function, that we have been discussed. And also we discussed that propagation of wave packet without distortion, that is in the so-called non-dispersive propagation, means after some times there is no spreading of the packet. We discussed in this section, or you can found this one in your first video. Okay, here we found that initially Gaussian it will be remain although it propagates without change in the shape and size. So there is no spreading of the Gaussian wave, Gaussian packet for this case, for non-dispersive case. So here I will be suggest one thing to you, that before you have to watch today's video, at least you have to go through last two videos. Okay. Also we have discussed that how a Gaussian wave packet is going to be spread. What will be the condition? That in last class, in our last class we discussed these things. Up to this much we have been discussed up to, and I also suggest that you have to write the note also. This will be very much useful for your exam. Okay, so up to this much we have been discussed. Okay, so here we found that this is represents the Gaussian wave packet which is moving along x-axis, and this equation number 5, or f xt mod square or psi xt mod square will be equal, and this value will be nothing but this much. This is equation number 5, and this equation number 5 corresponds to a Gaussian distribution function in the configuration space, or we can say this is giving the information regarding the probability density. So if we are going to draw this one, if we are going to draw these things, then we are going to find out this one. So let at x is equal to 0 and x is equal to t, it's x is equal to 0. Suppose at the origin we are going to be think that particle will be present over at the origin, means its corresponding peak, maximum peak will be observed here. If this situation will be at t equal to 0, then the value of the probability density, or the psi x mod square, will be pi by alpha. So if we are going to put t equal to 0 and x is equal to 0 in this equation, here in this equation, then here x is equal to 0, t is equal to 0, and t will be equal to 0. The whole term, this term will be 0, so e to the power 0 will be 1, and here this beta square, t square will be 0, means this term will be 0. So pi by alpha square root over will be pi by alpha, which will be the maximum value. Okay, maximum probability density. Okay, now what I am going to be discuss, you just carefully watch. Okay, this figure I explained in our last class video, and also today in this video I am going to explain properly. You have to watch, and I will be suggest one thing, that I will be suggest and somewhat request to you that this page, particularly this page is somewhat overwriting. You can found here some writing will be not clearly visible, but visible. If you can pause the video and you want to see, if you want to if you can pause the video, and you have to write one by one line. First you write the note, then you just go through the video whenever I am explaining the physics. So you just pause the video. See, it looks like somewhat overwriting, but you write down the each and every steps. This is the first line, second line, the next third line. This is these are the written things. Then after this part, this red line, the red letters also you have to write. Then after you have to write a at t equal to 0 from equation number 5. Then you have to write those things. This much somewhat overwriting. I will suggest to you that you have to write this much carefully. Okay. Now come to the this figure. So to explain this figure, I have been drawn this figure separately. It will be better that I can explain. Okay. So here this maximum probability density at x is equal to 0 and t is equal to 0 is equal to pi by alpha. Okay. Pi by alpha. But if we are going to consider this much, this is x square by 2 alpha. If we have to consider x square by 2 alpha will be equal to 1, then how much we are going to get? See this equation I am going to write over here. This will pi by alpha into e to the power minus 1. Okay, that means e to the power minus 1 value is 0.37. So it will be 0.37 of pi by lambda. That means here we consider that x square by 2 alpha. Here for this case we considered what? X square by 2 alpha will be equal to 1. If we are going to consider x square by 2 alpha will be equal to 1, then it will be e to the minus 1, and we are going to get 0.37 of pi by alpha, or we can say 37% of maxima. 37% of maxima. Okay. So if x square by 2 alpha will be equal to 1, that implies x will be how much? X will be 2 alpha root over plus or minus. Okay. So here we found that x is equal to plus 2 alpha root over and x equal to minus 2 alpha root over. So as this is our x axis, this axis is x axis and this is we considered at the origin at t is equal to 0. So 100% that x is equal to root over of 2 alpha will be this side, minus root over of 2 alpha will be this side. Suppose this point is corresponds to 2 alpha root over x equal to 2 alpha root over, this correspond to minus 2 alpha root over, suppose. Okay. So at this point the probability density will be how much? It will be 0.37 of maxima, or we can say 37% of maxima. So where we got the maxima? We got the maxima at the origin. At the origin we got the maxima. Here maxima is this one. So at this point, the value is reduced to 37%. It is reduced to 37%. Let this height or this value is 0.37 of alpha by pi by lambda, or we can say that this much height is nothing but 37% of this height. So at this point minus root over of 2 alpha, or at this point plus 2 alpha root over, we can get 37% value, and we are going to get the also 37% of the maximum value. Okay. So you can check also here. If you are going to put x is equal to, here you can put f, if you are going to put x is equal to plus root over of 2 alpha, then it will be cancelled out and it will be e to the power minus 1. Also if you are going to consider minus root over of 2 alpha here instead of x, also you are going to get that e to the power minus 1 and these things. And I suggest that you have to write step by step also in your note. Okay. So what we found, carefully you have to watch. I am going to explain these things because it is somewhat important and also somewhat tricky. At x is equal to 0, the particle will be here, and the so called maximum probability density, if we are going to draw, suppose this will be along x axis and y axis we have been taken as probability density. So at x is equal to 0, the probability density is maximum, that is pi by lambda, and at x is equal to either 2 alpha root over or minus 2 alpha root over, at this 2 point the probability density reduced to 37%. Okay. Now this width is nothing but called as wave packet. This width will be called as the wave packet between two reference point where the probability density reduced to 37% of maxima. This width is what? This width in between two points. What are the 2 points? This one is the point and this one is the point. 2 points where the probability density is how much? 37% of maxima. So this point and this point are to be considered as, you can say, one reference point. Okay. Now this will be the useful to understand the spreading of the wave packet that we are going to be discuss in this video later. Okay, this much you understood. Okay, next you come to the up to this much, this one. Okay, I explained this one. Next page, come to the next page, that if alpha k minus k0 square equal to 1, means here we have been represented this probability density in the configuration space. Suppose we are going to consider the k space, then we have to consider, so that means we are going to consider the first equation, this one, that is psi xt equal to minus infinity to plus infinity phi k e to the power I kx minus omega t dk, where phi k has been considered as e to the power minus alpha into k minus k0 square. So here this is nothing but the so called amplitude, and its multiplication with a complex conjugate, that means phi k into phi dash k will be give phi k mod square. This will be also called as probability density in k space. So only for that if we are going to put phi alpha into k minus k0 square will be equal to 1, then phi k, here see, phi k will be equal to e to the power minus 1, e to the power minus 1. So hence k minus k0, consider this one, the k minus k0 will be equal to plus or minus 1 by root over of alpha, or k equal to k0 plus or minus 1 by root over of k alpha, root over of alpha, and this k2 minus k1 will be nothing but 2 by root over of alpha. So here we can also say that in the k space the reference points will be this one, and that value are how much? This one, k0, this is, suppose this will be k0, this middle will be k0, so this will be k0 plus 1 by root over alpha, this point will be k0 minus 1 by root over of alpha, okay, and this width of the wave packet between two reference point, here I written this is the width, this is the width of the wave packet between two reference points where probability density is reduced to 37% of maxima. So here and here the probability density reduced to 37% of this maxima, okay. This second I is a representation of the same thing whatever we have discussed in configuration space, but this is in k space. So in your exam, if you are not going to write for the k space, only you have to write for the in the configuration space, also no problem, okay. Now we have to consider the wave function with time, wave function with time. So here psi xt mod square will be equal to f of xt mod square will be equal to how much? We have to consider the so called equation number 5. The equation number 5 is this one. Here this value f of xt mod square equal to psi xt mod square will be this much, and its maximum value will be when e to the power 0. That means when this value will be 0, then we are going to get this probability density or psi xt mod square will be maximum. So here the maxima or you can say maximum probability density at a particular time, or sorry, at a time t equal to 0, sorry, the maximum probability density will be equal to this much when it will be this much will be equal to 0. You got my point? That means this value f of xt mod square or psi xt mod square will be equal to 0 when this exponent to the power factor will be 0. That means alpha of x vgt square by 2 alpha square beta square t square will be equal to 0. Here you can found the corresponding position where we are going to consider that the maximum probability density we can found. So see here alpha, see from this equation it will be alpha into x minus vgt square will be equal to 0. That implies x will be equal to plus vgt. So it is telling that at the position VGT, at the position VGT, the maximum probability density we can found. Okay. Now suppose we are going to consider the peak. What I am consider the peak here. X will be equal to how much? Will be equal to Vg into T. Vg to T means it will be considered as one type of origin. Okay, where the maximum, where we are going to get the maximum probability density. See, I suggest here also you just carefully watch, patiently watch. This is somewhat complex topic, so patiently you have to watch once means you will be no problem for the second time. So now, but if we are going to consider this much value will be 1. Suppose this much value will be 1. That means we are trying to find out the reference point. Okay, what we have been discussed previously, that this point or this point are the so-called reference point where the probability density is reduced to 37%. So here also we are trying to find out the reference point by considering this much. See, if I am going to consider this much part will be 1, then it will be this much part will be 1, then it will be e to the power minus 1, or it will, we can say it will be reduced to 37%. Means we can give the language, or we can compare with the previous result by considering this type of these reference points. So here, if this will be equal to 1, let this is equation number 1, then we can found the probability density will be 37% of the maxima. Maxima is this much, and if we are going to consider this will be the 1, then it will be reduced to 37%. Okay, so now if we have to solve further the equation number 6, then we are going to get x will be equal to x0 plus this much. I told to you that VGT is considered as x0, means one type of origin. Here x0 is nothing but considered as origin. VGT is considered as origin. Okay, but plus or minus or both the side of this x0, we can found the two reference point where the probability density will be reduced to 37%. So here VGT will be equal to x0. So here this is considered as x0 position. Okay, so now right hand side of this point, left hand side also this point, we are going to get the two reference point where the your probability density will be reduced to how much? 37%. I am going to draw another figure for this discussion. Okay. So here you can see that this is your origin point, where origin point, or we are going to consider x0, or this is represented by or VGT velocity into the so-called time at a particular time. Okay, at a particular time with velocity, if we are going to consider that particular instant, will be considered as the so-called origin where the probability density is maximum. This is maxima. Okay, pi by alpha square plus beta square into t root over. And we are going to get from this calculation, we got the 2 points, that is x0 plus this much, x0 minus this much, x0 plus this much, suppose this point and this point, so where we can get 37% or 0.37 of maximum value, 0.37 of the maximum value. So this is the 2 point will be called as the so-called reference point, and this the width between these 2 points will be written as will be written as how much? 2 into 2 alpha by alpha square plus beta square t square root over. Okay, simple. This much minus of this much, you are going to get the del x, means this length from here to here between two reference points. So this is the width, this is the width. Okay, so this is the width of wave packet between two reference points where the probability density reduced to 37% of maxima. Okay, now further simplification we are going to do that del x t means at any time t, it will be alpha can be taken outside, it will be 2 into root over of 2 alpha root over of 1 plus beta square t square by alpha square, and let this 2 into root over of 2 alpha, we know that 2 into root over of 2 alpha is our del x 0. Okay, here see del x 0 is nothing but 2 into root over of 2 alpha, that only for that instead of this we are going to write del of x 0 root over of 1 plus this much I have been written, and this is equation number 7. Okay, now del x t will be in this form I can write, because del x 0 is this much, del x 0 to the power 4, del x 0 to the power 4 will be nothing but 64 alpha square, you can multiply. Okay, so this much to the power 4 will be 64 into alpha square. Because why I am going to do this, because I want to write alpha square here in the form of del x 0 to the power 4 by 64. Got it? Here I have been considered that del x 0 to the power 4 will be 64 into alpha square, hence alpha square will be del x 0 to the power 4 whole divided by 64, that I have been substituted over here, and this 64 can be go to the up, and this will be the equation number 8. You just match, maybe you written somewhere mistakenly something, it can be correct. Whenever you are watching the video, you just match your note wherever you have been written. Okay, okay, so come to the next. So from equation number 8, it can be perceived that increase of del x t or the so called spreading or increase of width is depends upon beta square. So from equation number 8 you can found one thing, that del x t, this width will be increased if beta square will be increased, obviously, because it is in the numerator. So if beta square will be increased, del x t will be increased. Now this figure, the same figure I have been written over here. Okay, this point and this point will be nothing but how much, actually this at time t, and this point you can write in your note, x 0 will be vgt, this will be this point x 0 vgt, and this point will be x 0 plus that factor, this one, and this one x 0 minus this one, you can write. So now let this is the simplification, further simplification we have been substituted the factors, nothing else. Okay, so let tau equal to alpha by beta. Now if we have to put in equation number 7, if you are going to put alpha by beta you will be equal to tau, then it will be 1 plus t square by tau square. So it will be del x0 root over of 1 plus t by tau square. Let it is equation number 9. So from equation number 9 it can be noticed that when t is greater than that of the tau, see, if t will be greater than that of the tau, then the spreading of the wave packet is significant. That means the del x will be significant, del x will be increased. Okay, if tau will be, if t is greater than that of the tau. But if tau will be very large than the t, if tau will be greater than that of the t, then this factor will be very less, very less. That means del xt is not going to be changed at all. So hence when it is written that when t is very less than that of the tau, then the spreading of the wave packet is very negligible. Okay. Now we have to another analysis we are going to do by considering equation number 7, that now again consider, this is one analysis, that consider equation number 7. Okay, that is del xt will be equal to del x0 root over 1 plus beta square t square by alpha square. Now put beta equal to h cross by 2m. Already we have been found that beta value is nothing but h cross by 2m, beta value. See, for non-relativistic electron we found beta equal to h cross by 2m. This value I am going to be put over here. So if I am going to put, instead of beta will be h cross by 2m, then del xt will be del x0 root over of 1 plus h cross square t square by 4m square alpha square, or further simplification I have been written this one. Let this is equation number 10. Okay, here mass, m is the mass of the non-relativistic particle. Okay, now from the equation number 10 it can be noticed that the spreading of del xt will be more for microscopic particle more for microscopic particle, means small particle, as compared with macroscopic object. Because if m is large, here m is at the denominator, if m is large, then this factor will be small. If this factor will be small, then del xt, or the spreading, or the the so called distance between the two reference point, which will be the indication of the spreading, will be not significant, will be very less. If we have to consider this mass will be very less, then this will be a significant factor we can get, and it will be add with 1, means that means del xt will be increase, we can say, or the spreading we can say, like that. So here microscopic particle means, suppose we are going to consider electron, proton, like that particle, with comparatively the macroscopic particle means one type of hard ball having mass is 100 gram, and here electron mass is how much? You just consider 9.1 10 to the power minus 31 kg. Okay, here this is 100 gram means 0.1 kg. So if I am going to compare this and this, this mass is very larger than this one. Okay, so for this mass, the del xt, or the so called spreading, will be negligible as compared with microscopic particle such as electron, proton, like that. As compared with macroscopic object, that is hard ball. So it has been calculated that so in theoretical manner it has been calculated that the width of the wave packet for 100 gram object spread by a factor of 10 to the power minus 19, a 29 factor Here I am writing the factor, there is no unit here is there. I'm going to show you, I'm going to say you what do you, what do you mean by factor. But after traveling 100 meter, on other hand, the wave packet width for 25 electron volt, having the energy 25 electron volt, spreading by 10 to the power 9 factor 10 to the 9 after traveling same distance 100 meter. So here factor means what, that suppose suppose you consider that for 100 gram object, so initially at for a particular suppose 100 for 100 gram object for a particular time, its wave packet width was suppose 1 meter, okay. So after traveling 100 meter, this width is increased to 10 to the power minus 29 of 1 meter. You understood what I am telling? So suppose 1 meter will be the initial, but after 100 meter traveling, the width will be increased 10 to the minus 29, which is very microscopic, could not be predictable visually, or it is, we can say it will be one type of negligible as compared with the mass, because the width of the width whatever will be increased, which will be 10 to the minus 29 factor, it will be very less as compared with the length of that object. At least suppose this will be the object and this is its length itself, and having mass is 100 gram. Suppose this object having the mass is 100 gram. Suppose this is the object having the mass is 100 gram, and when it will move to a distance 100 meter, its corresponding wave packet, suppose this is the particle, that means it is associated with wave packet is like this. It will be center at here, and this particle's wave nature is this one. It will be the center. So if it will move towards right, suppose 100 meter it moved, that means the wave packet also move with that object. But however, the wave packet will be increased, or the spreading of the wave packet will be 10 to the power minus 29, it will be very negligible, even if you are going to compare its diameter. But if we are going to consider one electron, if that electron will be move the same distance, suppose 100 meter, that is 100 meters, the electron will be move, that wave function or the wave function corresponding to that electron, or the width, actually the width of that wave function will be increased to the 10 to the power 9, to the 10 to the power 9, 10 to the 9, 10 to the 9. So it will increase of 10 to the power 9. So if the width will be this much, suppose, so its increase will be how much you just predict, it will be it will be in the factor of 10 to the 9. So only for that we can say the spreading of a microscopic object of the wave packet will be significant as compared with a macroscopic object. Okay, so this is the graphical representation of the spreading of the Gaussian wave packet. So this along x-axis we have been taken as the this is the x-axis along which the wave packet moves. These are the different times and corresponding different peak positions maxima. For this one, this peak is at here. The maxima of this peak will be here. The maxima of this peak will be at here. The maxima of this peak will be at here. The maxima of this peak will be at here, and it is moving along x-axis. At t equal to 0 will be this peak will be here. At t1, t2, t3 it is moving along this side, and this side we have been taken as probability density. Here you just carefully you have to watch. Suppose at t equal to 0 the probability density maxima is how much? This one, right? Oh, yes. The maxima of the probability density is how much? This one. Suppose this first peak, this and this, or the corresponding this point and this point is represents where the peak value is reduced to 37%. So at this point 37%, at this point 37%. So this is the width, width of the wave packet between the two reference point where the probability density is 37%. Carefully you listen. But after time t, after time t1, the peak is moved towards somewhat right. Okay. And if it is so, with time the peak height or the maximum of the peak will be also reduced. So that is also you can measure from here. See, this is represents at a particular time. This is the maximum value of a probability density. That means here at t equal to 0 the maximum probability density is this one. At t is equal to t1 the maximum probability density will be this one, t2 this one, t3 this one. This is gradually decreasing. It is decreasing or not, you can validate or you can verify from this equation. See, if t will be increased, this whole value also decrease. Okay, that means the maximum probability density will be decreased if time will be increased. That means if time will be increased, time increasing means the wave packet is moving along x-axis this side. So at a time t1 the maximum probability decreases. Okay, but its corresponding reference point will be found out here and here. Okay, this is the main thing, this is the important thing that you have to understand. First I am going to show you it. Okay, initially the reference point is where? This one, this 2 is the reference point and this is the width. Okay, this is the width initially. Next, when it is moved from t equal to 0 to t equal to 1, the maximum the maximum probability density peak is reduced from here to here. Okay, but the reference point where we are going to find out the probability density will be 1 by e or 37% of this one. This also that width will be increased. See, this, suppose this point we found that reference point for here, reference point here we found the reference point. For the second peak, this one I am going to put it in red. This one and this one is the reference point for second peak where the probability density is reduced to 37%. You just check it. This width and second width, this one, which one is the larger? This one is the larger than this one. Likewise, if we are going to consider third peak, the width will be further increased. This width, the distance between the two reference point. Then the next time this width will be again increased. So this is Gaussian wave packet spreading with time. Okay, so you should not be you should not be draw these things whatever I explained. For explanations whatever I drawn, you should not be draw. Initially what I drawn, that you have to draw in the exam and also your note. Okay, this is for your, I explained only for that I have been drawn this this width and etc. You should not be draw. You should draw only these peaks, only these 4 peaks, having increasing of its spreading. Okay, now this is another few representation that you have to know. It will be required for many places. At many places it will be required, so you have to also remember, or you have to know at least. Remember or not, that is depends upon you. Here you can see this is nothing but your what, psi x. This is your psi x. Okay, this is the so called the wave packet. How much spreading or the spatial spreadness is this much. Okay, the spatial spread or spatial length or coordinate or geometrical length, spatial length, geometrical length is the same meaning. Okay, so if we have to draw these things in k space, or if you have to draw, if you have to transform this one to the k space, means your wave vector space, then this geometry will be looks like this one. Okay, so here narrow function phi k, here written narrow function phi k obtained function, or you can say peak, obtained to a wave function psi x, to a wave function psi x with broad spatial extent. Broad means larger spatial extent. If I am going to reduce the spatial extent, which is this one, its representation, its k space, and this representation, the narrow spatial extent will be represented in the k space as a broad peak. Whenever the spatial extension will be large, then we are going to get a sharp peak in the k space. When the spatial extension is small, or we can say narrow, then we are going to get a broad peak in the k space. Okay, this is the Fourier transformation. That means this geometry having the Fourier transformation of this one, this geometry having the Fourier transformation of this one, or mathematically if you are going to be verify, you are going to get also same thing. Okay, so now I am going to be suggest one thing, that suppose in your question, in your exam, you are going to be asked that you have to write the spreading of Gaussian wave packet. Spreading of Gaussian wave packet means from here you have to start B. From B you have to start. Yes, from B you have to start, and I will be suggest that as much as possible you can squeeze the mathematical derivations. Okay, so this page you have to write, and this page also you have to write, and this page, these writings you have to write. Up to this much you have to write. K space, representation in the k space, no need to write. And this one, these things you have to write also. These are the also required. These all the things are also required. And here you have to stop. Equation number 10. This discussion you should not be discussed in your exam. Okay, so this is the representation. This is the representation of the wave packet with respect to the mass. Or if you can stop your writing over here also, no problem. Here, this equation number 7. This equation number 7 also represents the so-called spreading. Okay. So if in the question they have been it is asked that how it has to be spread with respect to mass, then you have the equation number 10 is required, and you have to draw this figure with time. With time, how the initial wave packet is spreads with decreasing its probability, maximum probability density. Okay. So thank you so much for watching this video. Thank you. You go through this video carefully and ask me wherever you have a doubt. Thank you.